Okay. I don't mean to interrupt you. I'm ready now. So go ahead and work on that a little bit. I'm going to put it on the board, and I'll put some questions down there. We'll take them in order. So work from the top. This is basically what we did in the afternoon class. And then at the end of this, I'll take some questions. And certainly if you have related questions as we go through it, feel free to speak up. Let's do, well, so if you're still working on the chair and the bond line, that's fine. Let's get down and do the top five there. Actually, we may do all those questions there. So if you haven't, I'll give you a couple more minutes. Look at these questions in particular if you haven't already. And we'll do those first. But they're kind of chapter 1 and 2-ish. And you can ask questions during this phase as well if you want.
What's the formula again for like chemical compounds? Is like C something?
It's for organic, it's always C whatever, H whatever, and then the rest of the elements in alphabetical order.
Oh yeah, isn't there like a math one though?
Oh, okay, yeah. Actually, yeah, sorry. That was another one I meant to put on there. All right, so units of unsaturation. If you have a structure, you don't want to use the formula. All right, so there you can mathematically, it's probably in the spectroscopy chapter. You're not going to have to tell me how many units of unsaturation based on a molecular formula. But you will have to tell me based on a structure. So you have that. But like a saturated hydrocarbon is CnH2n plus 2. All right, so if you think about a zigzag, right? All these are CH2s. Every one of those carbons has at least 2 hydrogens on them. The end carbons have one additional one. So that's the +2. So an unsaturation, every unsaturation basically pulls 2 H's out. So one unsaturation would be CnH2n. 2 unsaturations would be CnH2n minus 2. The N and the 2N are like the subscripts. You guys at home can fast forward, well, or work them. I'm just talking to the camera. All right. Are there any functional groups in this molecule that you guys are supposed to know? What is it? What's that? And I would say amine, but yeah. So it's not, and that's a tricky one. You're basing it on the end. And you guys should check out. So an amine is going to be a nitrogen with 3 bonds. Those R's can be carbons or hydrogens, but it's got to be 3 different things. So that one you wouldn't actually have to know. And I wouldn't put this one on a test. So if you go back and look at I shouldn't say a test. I wouldn't put this on Thursday's test. Hang on a sec. So what is it? Amines, alcohols, alkyl halides. Actually, I should stop there. What were you going to say?
I was just gonna name them.
What's the other functional group?
I know the ones on
The ones you have to know, or the ones?
in that one.
Which one is? Yeah.
I see an alkene, an alkyne, and
So okay, so ether is not on the exam 1 list, but that is in fact an ether. You said an alkene?
yeah.
Where's the alkene?
Does it? It would be attached to the nitrogen. I'm not sure.
Yeah. So I have tripped you 2 up on this. All right. So again, that I'm not trying to think how to phrase this. I have now written the exam, so I don't want to give too much away. I'm not I'm not going to put a molecule that has functional groups. So like I've done here, okay? So immediately you guys come in here and I'm like, what are the functional groups? And I looked and I'm like, crap, there's 2 there that you don't have to know. This one is actually called an imine, I-M-I-N-E. And it's sort of because it's a cross between an amine, and I don't know where the I comes from. It's got double bond character, but it's not an alkene. An alkene is carbon-carbon double bond only. An amine, 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 I've heard all these, is a nitrogen that's got 3 other things around it, but it's not an amide. So you should take a look at if you haven't, look at the class from early today. There was a functional group in there, and I did the same thing to them. I put a functional group they didn't have to know in there.
Yeah, which ones are the ones that we have to know?
So the only functional group in this molecule you have to know is this one, which is an alkyne. Any molecule where I ask this question on Thursday, I'm not saying I'll put everyone you have to know on there, but the functional groups that are on it will, I'm not going to put functional groups you don't have to know yet on it. Carbon-carbon triple bond is an alkyne. An ether is just an oxygen with 2 single bonds to carbon. And then, yeah, that was probably a dirty. I wanted something. There's a reason that functional group is there. It's for the last question on the list. Sorry about that. All right. Put in lone pairs where you think they ought to go. Lone pair? There is a lone pair on the nitrogen. There's one. So that nitrogen is neutral. Neutral nitrogen is going to have 3 bonds, 1 lone pair. All right, what else?
This one on the negative carbon.
A negative carbon, the only way to have a negative carbon is to have a carbon with 3 bonds and a lone pair. All right? 2 on the oxygen. Any others? No. All right. So that's it. So neutral, and again, I have to give you the charge. The only reason I would ever draw a molecule that has charges, and I wouldn't put the charges on there, is if I'm asking you where the charges are, right? So this is kind of an first exam in Orgo 1 kind of question. You know, here's a molecule. The other thing I have to tell you in that point is, here's a structure. All the atoms and electrons are shown. All right? I can't ask you where are the lone pairs and where are the charges, because then you can just do whatever you want, right? You can draw a lone pair in and tell me it's negative. You can not put it in and tell me it's positive. You can tell me there's hydrogen. Like if I don't tell you all the atoms and electrons are there, you can't do the charges. Okay. For now, let's skip molecular formula. And do we have any sp2 atoms? The nitrogen is sp2. It's got a double bond. It's attached to 3 things if you count the lone pair. Lone pair, carbon, carbon. Yeah, so that one is also. And that's it, right? So sp2 carbons are going to pretty much have 1 pi bond. When we get there, we'll look at positively charged carbons later in the semester. You will occasionally see sp2 carbons that have a positive charge, that aren't double bonded to anything. But right now, we'll leave that out. Basically, an sp2 carbon is going to be a double bonded, an sp2 atom is going to be in a double bond. It's going to be trigonal planar. All right, do we have any sp atoms? Okay. You said the one? Yeah. Which one of how many atoms are in that triple bond? Atom there and an atom there, right? No, I'm bringing it up. I'm not picking on you guys. I will try. I don't mean to pick on you. I've taught this. This is like probably the 20th time I've taught Orgo 1. God. I see common things. Students they see 1 atom. You guys a lot of you will see 1 atom in a triple bond. I don't know why. I never did that one. A lot of the mistakes people make, I'm like, yeah, I did that. But a triple bond is always going to be 2 atoms. All right, so coming off here, you've got this carbon bonded to that carbon, bonded to that carbon. So 2 sp atoms up there. Okay, so we've done that. We've done lone pairs, done functional groups. Anybody got a molecular formula worked out? All right, let's hear it. C12H18 NO. The NO is right. Don't miss that, all right? That's it. So, and technically you should put the negative there.
Oh, my
Yeah,
bad.
no, I didn't remember it until I saw it on the ChemDraw thing. So if you work through this, I'll point them out in case you got something else. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The N and O are stand out. I'm going to work the other way here. 1, 2, nothing. 3, 4, 5, 6, 9, 12, 14, 16, 17, 18. That one gets forgotten a lot, right? There's a carbon there that's got 3 bonds, so it's got 1 hydrogen. I shouldn't make light of it. I'm going to take points away from people for doing that. But I was like, I got to 14 and I'm like, I'm bored. So I need to know that you can do that. Once you establish you can come up with a molecular formula, I will try not to ask you that question a whole lot. All right.
Is there a faster way to count hydrogens?
No. Yeah, there's... why did I... no, there's really not a faster... There is... Well, I don't know if it's faster. So if let's say this... Probably for this molecule, it's not faster. But there is this formula. Like the number of unsaturations is 2 times the number of carbons plus 2 minus the number of hydrogens minus halogens plus nitrogens divided by 2. Again, you don't have to know that. And I have to like work it out every time I do it. So if you know the number of unsaturations and you know the number of all the other atoms, you can solve for H. And that probably is only faster if it's an enormous molecule, right? Like counting carbons and nitrogen and oxygen is pretty easy. Straightforward. So coming up with that molecular formula. Anyway, how many units of unsaturation do we have? Anybody disagree with 4? Got a 3. We're tied 1 to 1. 2. We are really spread out. Another 3. 4. Does anybody think 5? Does anybody think 1? Well, I don't know what I did there. Yeah, so when you're teaching and a student does that, normally you like it, but now I'm like, I don't know. I get 4. So units of unsaturation, if you have a structure, it's a ring. Rings are an unsaturation. Pi bonds are an unsaturation. You have to count every pi bond. It's not that there's a pi bond there. So 1 pi bond, 2, 3 pi bonds. Carbon-carbon triple bond is a sigma and 2 pi's. So that's 3 pi bonds in a ring. That's going to be 4. If you do try to use, and so we probably will use that formula, 2 times carbon plus 2 minus, we'll probably use that in the spectroscopy. And what I will tell you is the number of unsaturations is always an integer, right? You can't have half an unsaturation. All right, is this molecule chiral?
Yes.
Yeah. Right, so this carb, let's just start, let me number these. I'm not going to number these in such a way that they're like how I would do for nomenclature. I'm on it. Honestly, I have no idea which carbon should be 1. All right, one of the carbons in the ring should be 1 here. Ideally, I think you'd make it one of these 2, because then it'd be 1, 2, 3, 5. But it might be that this group takes priority. Double bonded things often take priority, and that has to be 1. Then it becomes 1, 2, 4, 6. You would not have to name something like this, all right? But just to keep tabs on things, I'm going to number the carbons in the ring. And then we can use those as reference. So carbon 1 has an sp carbon, an H, a CH2CHO, CH2CHC, right? You have to go a ways, and you always have to keep going, all right? You can't just say, oh, they're both bonded to sorry. You can't just say C1 is bonded to two CH2s, and so those are the same, so it's not chiral. The CH2s are bonded to something, those are the same, then you go to the next thing. If those are different, if at any point it's different, then it's different. To determine that the two groups are the same, you have to go all the way to the end of whatever chain or group, or in a ring, you have to get back to the same point. Yep.
So, like, if, for example, like number 1 is chiral, if you're counting, 3 has a methyl and obviously 5 has an oxygen, with 3, would you go up to hydrogen and say, like, oh, it's different? Or would you keep on going to 4?
You go both ways, right? So C3 is different than C5. C3 is a CH bonded to a methyl. C5 is a CH bonded to an O. Those are different. That's what I mean. It just has to be a little difference. Yep.
So when it asks to do like absolute configuration for all the chiral atoms, you have to go through like the entire range of all 6 of them?
To do so all six. I don't guess I got.
Like for all of them that are like, so there are like 4 in the ring that are chiral, so you have to do like RF for all of them?
Yeah. Well, I mean, on this sheet, yeah. You don't have to do RNS unless I tell you to do, or ask you to do RNS. So yeah, there are 4 chiral centers. C1 is chiral, C5 is chiral, C3 is chiral, and C4 is chiral. Okay, so I'll put a little star by those. That's a pretty common way to indicate a chiral center. And so there are chiral centers in the molecule. So if there is a chiral center in the molecule, if there's any chiral atom in the molecule, the only way that molecule is not chiral is if the chiral centers offset each other. And the only way they can do that is if like the 2 or the 3 or the 4 chiral centers are all bonded to exactly the same thing. Right? And you will see this, that the molecule will be very symmetric. Okay, so the classic examples are going to be something like this. Right, so that molecule has a plane of symmetry. It's got 2 chiral centers. This carbon's bonded to a nitrogen, an H, a CH, and a methyl. That's 4 chemically different groups. Right? But if you look at it, this other chiral center is bonded to the exact same things, an N, an H, a CH, and a methyl. And so the asymmetry of the 2 atoms offsets each other. You see this in a plane of symmetry, right? Left side of this molecule reflects exactly into the right side of the molecule. So if you were to like, I use this analogy somewhere, maybe a PowerPoint show. It may be a crappy analogy. But I always like to talk about your reflection, right? You are a chiral object. You are not superimposable with your mirror image. You can't put you know it immediately if you put a left-handed glove on a right hand, or a right-handed shoe, a right-footed shoe on your left foot, right? I don't know, that's a sick feeling. Like for minor things, like I hate that. So, but imagine your hand was not asymmetric, right? 2 thumbs, index finger on either side of your middle finger, right? Perfectly symmetric hand. Is that weird? Is that too weird? Like but then you just have a glove, right? It wouldn't, and when you reflected, like you'd have a plane of symmetry then. Your 2 hands were the same. Like you could imagine 2 feet being the same. They're not curved at all, just square feet. I don't know. Biology's weird. I can see it. If that happened though, right, you'd have a plane of symmetry down the middle of your body and you wouldn't be chiral. So you should be able to see it. Like if you find a molecule that's got a chiral center in it, and it doesn't look super symmetrical, like that looks really symmetrical, I hope you agree. This molecule right, which looks really similar and looks pretty symmetrical, is actually chiral. Like there's not a plane of symmetry there. And if you draw the mirror image of that compound, they're not superimposable. John, you had a question?
Yeah, is the one on the left cis?
So you can't say it's cis or trans if it can rotate. This is actually really complicated. It's way easier to teach this if we make the thing rigid, put it in a ring. Now you can call it cis, because there's no way for those nitrogens to get on opposite sides of the ring. The top two can rotate around that bond between the two chiral carbons. And so if you say they're cis, well, they're cis in this conformation. There are other conformations where they're not, so there's no cis and trans there. Cis and trans requires either a ring or a rigid double bond. Okay, so this molecule is chiral is the point of all that. Right? Chiral centers exist in the molecule. There's no plane of symmetry. This molecule is not very symmetric at all. All right, next question is how many stereoisomers are there? And I heard somebody say something that will help. Hang on just a second. So first of all, how many chiral centers are there? There are 4 chiral centers. For exam 1, because we got a snow day, you don't have to know about isomerizable double bonds. This double bond actually could isomerize, but let's just imagine for now that it can't. And don't worry, but if that doesn't make any sense to you, don't worry about it. We'll get to it in the next unit. So 4 chiral centers. If they're independent of each other, each one can be 2 different things, R or S. There are only 2 options for a chiral carbon, a tetrahedral atom. There's only 2 different ways to draw them. All right, so the answer to this is 2 to the 4. How many different answers do I get if I ask how many that is?
Too many.
We can vote on this again. Anybody got a number for 2 to the 4? No, I reserve the right. Look, professionally, I am not supposed to make fun of you. And it's so much harder now because everything's recorded. I'm recording all this. Like, it's killing me. Before the pandemic, man, I just ripped people. You can't see that I'm smiling. And I'm off camera, so you're going to tell people I'm looking mean here. Anybody disagree with 16? So, no. And look, I will not make fun. I won't. I sincerely, self-confidence is hard. It's much easier to lose than to earn. But I promise everyone in this room, right? You're bright. You got into Wake Forest. You got into organic. Like, you can do stuff. You will also do massively stupid things in your life, all right? So I remember one exam a few years ago, 2 to the 5. And somebody was like, that's 25. They just like added it. And like, yeah, you're all laughing, but I promise you will do, like, I would do, like, I've done stuff like that. And it's just like, it's probably, I'd called 30 seconds or something, and they're just like, 2 to the 5, 25. Yeah, that's fine. And they didn't write 25 in such a way that I could surmise that, oh, you meant this to be a superscript. They actually wrote 2, superscript 5 equals 25. Look, if you do, so what I would say is, if you're not confident in your ability to multiply 2, come on. But also, write 2 to the, like on this problem, if you write 2 to the 4, and then, I don't know, you write 42 or something, like, I will probably make a deduction. I will certainly kind of like draw a smiley face by it. But the point is, I want you guys to know, the point is here, you have 16 different stereoisomers because each one of these chiral centers operates independently. If something ties them together, or if it becomes really rigid, like, I don't know, say this carbon was bonded to that oxygen, right? Now they can't flip around. Those are now not 2 independent chiral centers. So that, and then you could have meso compounds, right? So Like I could change these both to dashes, but I would get the same compound. So that reduces how many stereoisomers are. So this equation that the book gives you is like a maximum. This is the maximum you're going to be able to have. So we're going to get to the next things here in a minute. I'm going to give you another few minutes to work. We can have 16 stereoisomers. So this molecule's chiral, which means it's got an enantiomer. How many enantiomers does it have? 1. Anybody disagree with 1? The enantiomer is a mirror image. Everything has one mirror image. So no molecule has more than one enantiomer. So this molecule has an enantiomer, and then it's got 14 diastereomers. Because remember, this molecule is actually one of the 16. Okay? So if you haven't already, draw the bond line structure of this cycle. Oh, we haven't done the chair flip yet, have we? I'll give you a few minutes. Work on the chair flip. Work on the bond line. Draw the enantiomer. Your enantiomer and then draw one diastereomer, constitutional isomer. Constitutional isomer is pretty easy. What was I going to say? You can draw your enantiomer either as a chair or a bond line. I'll tell you what, if you've already done that, draw it as the other one. Right? If you drew your enantiomer originally as a chair, draw it as a bond line. If you drew it as a bond line, draw it as a chair.
Wait, you said that there's 14 diastereomers, 1 enantiomer,
And then this one.
and then what's that?
So yeah, that 2 to the 4 includes that structure. Right? And it always does. I've given credit before when people say 15. Like if I said, how many stereoisomers does this molecule have? It has 15, actually, because it's one of them, right? Like that molecule plus 15 others. If you tell me 16, there's not 17 of them. I don't really care. If you say 15, I'll know what you mean. If you say 16, I'll know what you mean. I'm not going to get. But just remember that this structure is one of the 16. Sounds like a war film. Help you guys out on this bond line.
So then is that achiral molecule still an enantiomer?
No, so because it's achiral, it doesn't have an enantiomer, but it can have a diastereomer, right? So if it's achiral, it means something that is achiral is by definition superimposable with its mirror image. So no enantiomer for this one. These 2 molecules are diastereomers, right? Because now you've changed one, not changed the others. So there are a lot of achiral compounds that have stereoisomers, but they're always diastereomers. Okay, let's do the chair flip first. So a really important piece of just terminology here. Chair flip. Whoever came up with that phrase, well, I don't know, they're probably dead. But if I were them, I would regret it. All right, they probably never had to teach Orgo 1. A chair flip has nothing to do with turning the molecule over, turning it around, rolling it over. It is a conformational change. It's a bond rotation. All right, so when you do a chair flip, right, there's 3 up carbons here. So an up carbon is where the 2 bonds going to it are pointed up. There are 3 down carbons. I tend to refer to the up carbon on the left or right as the up carbon, the others, and then you've got the front, just reminding you of this. 2 and 3 are in front of the plane, 5 and 6 are behind the plane. All right, in a chair flip, the 3 up carbons move down, the 3 down carbons move up. So the chair itself has to change. If you draw the chair exactly the same over here and just switch equatorial and axial, you'll in fact draw the enantiomer. It's a pretty good way to draw the enantiomer, in fact. Right? In the enantiomer, you're going to change every chiral center. So if I keep the ring exactly the same, move this group down, move the methyl down, move the ether down. Good Lord, they're all up. Move the alkyne down. I've got the enantiomer. I've changed every chiral center. All right, so that's not a chair flip. Cyclohexanes aren't sitting there going back and forth between them and their enantiomer. So carbon 1's got to come down, carbon 4's got to go up, 5 and 3 go down, 2 and 6 go up. All right, I'm going to number these carbons. I'm going to put the numbers in exactly the worst spot. All right, so there, right, 2 and 3 stay in the front, 5 and 6 stay in the back, 1 and 4 stay in the plane, 4 goes up, 1 comes down. All right. The alkyne, which on the right is up relative to the H. All right, so the alkyne is up, the H is down. And I am saying this with reference to the board and to the earth. All right, alkyne is up relative to the H. That molecule has no sense of this whiteboard or really gravity, okay? There's no up and down in a molecule. There's no left and right. So you can choose whatever perspective you want. And I think I've confused a lot of you. Confusion is kind of a necessary element of learning. But I'm going to try to clear that up now. So you do not have to look at these molecules left to right. You don't have to look at them from the front or the bottom. You don't have to be standing upright in gravity, right? You could view it as upside down. But you have to pick a point, anchor your eye there, and then once you do that, it can't change. All right? You can't kind of drift around as you draw the molecule. And so I'm looking at this side on. Really, a chair is just looking at the side of a cyclohexane. A bond line is looking at the top or the bottom. Okay, so 2 and 3 are in front, 5 and 6 are in the back. Alkyne is there. Alkyne's going to stay up relative to the H because we're not breaking any bonds. All right. Carbon 3, again, still in the front. Methyl is up. H is down. Carbon 4, this amino group is up. Imino, it's the Oklahoma. You can't tell. I actually got yelled at. When I went to grad school, I say imine, I-M-I-N-E, the same as A-M-I-N-E. What are you going to do? Okay. So the up nitrogen-containing functional group goes up. H is still down. And then you've got a methoxy group on 5. It's going to be up. H is down. So there's the chair flip. The chair itself has to flip, but you're not flipping it over. It's a conformational change. I will try going forward. I say this every semester. Like if I'm going to flip a molecule over like a pancake, I will try to say I'm going to turn it over or roll it over. Because chair flip you're completely forgiven if, as an English speaker, you hear chair flip and you're like, we're going to flip the thing over. That's not what's going on. It's a conformational change. Up carbons go down carbons go up. Axial turns into equatorial, equatorial turns into axial. But everything stays on the same carbon. The front carbons stay the same. The carbons in the plane stay the same. The back carbons stay the same. Yes?
So like in the drawing on the page, it's like a different chair, obviously. If
Yep.
you did it that way, would you just flip the axle equatorial?
Like, I try so hard not to confuse you guys. No, I drew this.
Yeah, that's right. But I was saying if, because I see how you took one side, obviously, you chair flipped it. One side went down, one side went up. But in this, like, there's not really like a side to go up and down. You threw it. Like, I might just have to show you.
The left hand up carbon goes down in the chair flip.
Yeah.
The right hand, I mean, I'm not, look, my art isn't good. All right, but here's, I'm not saying I draw well. I would never pass Dr. King's class. All right, so carbon 1 is up. It's the left hand up carbon. My 2 and 6 aren't quite in the right place, but they're there. Like, they're not angled as much. And then 3 and 5, I botched 3 and 5 pretty badly. 3 and 5 are botched. I totally get that. But this basically means the same thing. They're in front. 3 and 5 are up, so in the chair flip, they're going to go down. All right? So the thing I heard that is making me really belabor this point is, no, you can't just change equatorial and axial. You have to change equatorial and axial, but you also have to change the chair itself. All right, so let's do that. You guys okay if, actually, I tell you what, I've got all these boards here for a reason, right? So let me just draw. So the chair is the same. I mean, it's not because I can't reproduce my drawings. I also can't sign the same. I can't sign my signature the same. So if anybody wants to like steal all my money, it's fair game. All right, so the chair here, I've drawn it exactly the same. Let me now switch that. 2 and 6. So I drew the chair exactly the same. And then I switched out, on every position, I switched out axial and equatorial. I just did the next thing you're supposed to do. I drew the enantiomer. All right? The other way to draw the enantiomer from the chair would be to just say, here's a mirror image. Like, draw the mirror image of that if you're good at that, if you like that. I'm just saying, like, if I gave you this, if I gave you a question, here's a cyclohexane in a chair form, draw the enantiomer. And I don't give you any more instruction than that, you can just draw the mirror image chair. You can draw the chair the same, switch axial and equatorial on every chiral carbon. Those get you the same place. You don't have to convert it to bond line. You need to be able to convert it to bond line because you don't know what I'm going to ask. But if, don't make it harder than it is. The more things you do, the better the chances you're going to screw something up, either because you don't know it or just because you're moving fast, stressful situation, and you make a mistake. All right, bond line. We can put that here. Okay, so any questions about drawing the chair there? I don't want to blow through that too fast. Basically, what you have to do is
It's an alarm. I didn't realize.
No, it's fine. I'm gonna probably be wondering for days why you have an alarm at 6:50, but okay. All right, so your chair in a chair flip, a conformational change. All the ups go down, downs come up. Oh, the other thing I was going to say, you can't actually flip the molecule. This is what I think what I was wanting to say. There are a lot of questions of this on the cyclohexane quiz. Wedge doesn't have to be up, dash doesn't have to be down. All right? For most of the time, and it's not weird that my students tend to think this, right? I'm not, my PhD is in aromatic photochemistry. You'll see aromatic chemistry next semester. Aromatic molecules are flat. They're all trigonal planar. There's no chirality. It's very simple, little flat molecule. You can draw it from all, like from the side, it's a line. So, I wouldn't say I struggle with this. This is not completely natural to me. All right? So I tend to always be like, I'm going to look at everything left to right. I'm going to look at it from the front, and my head is up. All right? But that molecule does not know that. And so, especially for an achiral cyclohexane, okay? So I think the one, let's just do this. All right, so there you go. Now let's make it a real molecule. You guys are all going to think that, the wedges have to be up. And this molecule is achiral. There's a plane of symmetry right here, and you were kind of asking about how far you have to go to see if the bonds are the same thing. So if we take the carbon with the OH, it's bonded to O, H, okay, those are different. C, that's different. C. CH2, CH2, that's the same. CH2, CH2, that's the same. Then they're bonded to the same carbon. So it's the same either way you go there, right? And you have to go until you get to a point. If I add anything, right, these just became chiral centers. Okay, so now you draw your chair, and it's easier with an achiral cyclohexane. If you're aware that wedges don't have to be up. Actually, given that the way that quiz was done, multiple choice, here are your only choices, and I gave you a none, I think the none probably suckered a lot of you in. So if I just ask you to draw it, maybe you do it just fine. You're like, well, okay, OH is up, isopropyl's up, bang, you're done. That's the most stable cyclohexane right there. All right? It's the most stable because both groups, so cis 1,4 cyclohexanes, they can't both be axial, right? Or sorry, they can't both be equatorial. OH is axial, isopropyl's equatorial, isopropyl's the bigger group. There you go, that's the most stable one. This molecule that's the same structure. All right, and this is what messed you, I shouldn't say all of you, this messed a lot of you up on the quiz. Right? You're like, the wedge is up. That one's not there. So it's going to be the other one. To take the bottom chair and turn it into the top chair, I just have to roll it over. All right? Not a chair flip. A chair flip would turn the OH into an equatorial OH, the equatorial isopropyl into an axial isopropyl. I mean, roll it over. Right? If I just take this thing, do that, it lays perfectly over this structure. Right? So these are the same. This bottom one, a wedge is down. And it just means like I'm floating in the flask upside down, looking at the molecule. So achiral cyclohexanes are a little simpler. You don't have to keep track of like where the thing is. Is it on the front carbons or the back carbons? Okay, so having said that, any questions about what I just did there? All right, so turning the cyclohexane into a bond line. Like I said, first thing, draw a 6-membered hexagon, single-bonded cyclohexane ring. Now, you have to decide where you're looking, but this is already given to you. When you draw the bond line, well, actually, you don't necessarily have to, but the chair is telling you where you are. All right? 2 and 3 are the front. could be any one of these bonds, right? I could be looking here, and this is 2 and 3. I could be looking here, and this is 2 and 3. I can also decide, is it 2 and 3 or 2 and 3? Right? If I do that, though, then things move around. So as I'm looking here at 2 and 3, I've got 2 and 3. 1 is on the left, 4 is on the right. And, you know, like I said, I'm almost always going to stick my eye, so I'm looking left to right. You don't have to. You could just as easily look this direction, you could look this direction, that direction, here, here. And what that really amounts to is, once we get our bond line structure drawn, any structure, once you have any structure, you can rotate it an infinite number of degrees in a circle. You can turn it over an infinite number of degrees front or back. All right, so if we do this, if I'm looking this way, again, these are the front carbons. So this is 2 and 3. 1 is to the left, 4, 5, and 6. All right. So then I've got an alkyne that's up. By the way, some of you would inevitably draw the alkyne that way. It's exam 1. I'll certainly make a note of that. I don't know if I probably wouldn't take any points off for it at this point. But don't do that. sp carbons are linear, not bent. All right, carbon, and if you do your numbers this way, now you've got it. Carbon 3 has an up methyl. Carbon 4 has this up weird group. Carbon 5 has an up methoxy. All right, one sec. I should say, if this methoxy were just a methyl, this would have a plane of symmetry, right? What were you going to say?
Does it matter when you're drawing that, which way you draw the nitrogen going?
Yeah, I've been really careless with this. So I said this is an isomerizable double bond, right? So on the carbon-nitrogen double bond, you've got carbon 4 and the negative charge trans. I've been noticing, I've been drawing them cis. Is that what you're talking about?
Like if you just have the double bond going straight.
Could go that way?
Yeah.
So the double bond going that way is rotating around a single bond. That'd be all right. Right? Like I can rotate around the carbon 4 sp2 carbon bond. I can rotate there, so the nitrogen double bond could be over here. It's a little harder to rotate around the double bond. John?
Is it okay to make the nitrogen one? So that way, like, everything would be like the nitrogen be on top and then
So make nitrogen.
well, the carbon one, make that instead
Make-
of nitrogen one, carbon one.
Could if you, I mean, it doesn't matter. Like I didn't do this for nomenclature. I did it to keep tabs on things. So you can't do that. Having drawn this as carbon 1 over here, I can't decide over there that carbon 1 is going to be. But now, like I said, if I can turn this molecule however I want. If I can do it artistically. 180 degrees ought to work. No. Maybe I can. I've just turned it 180 degrees. Okay, that's the same structure. You could turn it 60 degrees, you could turn it 120, you can turn it 17.2 degrees. None of that matters. What matters is that once you've established, all right, the chair itself is telling you these are the front carbons. I've said that's 1 and that's 4. So once I've done, and you could have at the beginning said this is 1. That would have been fine. All right. Okay, so now, if you were to draw a bond line enantiomer, same thing. This chair is the same as the chair up there. So the bond line here, there's my 6-membered ring. Again, I'm looking this way. So alkyne is down. Carbon 3, the methyl is down. Carbon 4, that's going to bug you. It's going to bug me. And then carbon 5. Right? So you can see by doing this chair, by by holding the chair the same, changing the axial and equatorial, I get the enantiomer, right? So here, if you overlay these, everything overlays, all the wedges turn to dashes. There aren't any dashes, but dashes would turn to wedges. Make sense? All right. Man, where are we here? Other chair, stable. Did we do stability? Did I ask? Which of those two chairs? Remember, chair flips are conformational changes. So the molecule really is going back and forth. Chair on the left exists, and if you were to follow that one molecule around, it would occasionally turn into the molecule on the right. Then it'd go back to the molecule on the left. Back and forth, back and forth. If you look at the whole population, you'd have some on the left, some on the right. It's not going to be 50-50, though. The more stable one, any given molecule will spend more time in the more stable conformation. Most of the molecules at any given moment will be the more stable one. So which one is the more stable one? How come? Right, so there are 4 groups. 3 on the right, 3 are equatorial. Alkyne, methyl, methoxy. 1 is axial. They're all kind of roughly the same size. So you can really get down in the weeds with if you're right, by the way. The one on the right is most stable. 3 to 1 is pretty hard to overcome. The only way the 1 equatorial, 3 axial is going to be more stable is if the 3 are really small and the 1 is gigantic. Okay, and that's not really the case here. They're all more or less the same size. On the exam, it probably wouldn't even be this speculative. Like maybe you could imagine like maybe there's something weird about a negative charge that it would rather be, equatorial. Like it's really important it's equatorial. There's not, but it'll be really straightforward. All right. Now, is there a diastereomer of this molecule that is more stable than the original molecule? Got some yeses. What would have to happen? Well, it would have to be in this structure. Yeah, so it would. So it would have to be equatorial. Like if all 4 are equatorial, that would be more stable. So, yeah.
I have a general question.
Yeah.
So, like, do you want us to draw the H's when we have a substituent?
Probably you should. And what I would say is, if it's absolutely clear to me what the group is, I'm fine. And some of you will have seen that on the Chapter 4 worksheet that I didn't grade those super carefully, but I tried to make comments. And a lot of times you'll see chairs, I'll see chairs. Right? Even uglier than the chairs I usually draw. And then it's just kind of a line there. Or, like there's nothing there actually. And so if it's not really clear what, I would go a step further. Not only would I draw the H's in, like really I would be like axial, A, E. Because again, I mean, I don't care so much about your artwork. I want you to be able to draw molecules that are, other people can interpret. But I really want you to know groups go equatorial, and you'll figure out the artwork. All right, so I put these in just sort of for clarity. That's definitely, I think the axial ones are easier to see, like straight up and down. Again, it's straight up and down. If you draw your chair sort of cockeyed, now it's not necessarily straight up and down. right? Okay. Yeah, so the diastereomer, oh, what I was going to say is diastereomers can have different energies. Diastereomers are more like, diastereomers are easily separable. You're all doing chromatography in lab, or most of you will have done by now. Like on TLC, you can separate diastereomers by TLC. They have different properties, polarities. They're like different compounds. Enantiomers have identical stability, unless they're interacting with something else that's chiral. Okay? So, like a chiral drug will be equally soluble as its enantiomer. It'll have the same boiling point as its enantiomer. It'll have the same RF as its enantiomer. Have the same spectrum as its enantiomer. Put it in you, and the two enantiomers will behave very differently, right? Because you're chiral, and all the biochemistry that's going to metabolize that drug is chiral. So now one enantiomer, you know, may be a great anti-nausea med, and the other one a mutagen. Real story. We'll talk about it later. Okay. Did stability. More stable. Bond line, functional groups, lone pairs, formula. So we've established that diastereomers exist. Let's draw that. I've basically said that. So the more stable diastereomer, and I think this is what you said, we can just take, so here is our original bond line. Oh, look, I'll do it here. All right, that's a more stable diastereomer. And you should see a relationship here. The book mentions this. I think my PowerPoint shows. I don't know if I've said it in class. On a cyclohexane, a 1,3 arrangement, they can both be equatorial if they're cis. 1,4 and 1,2 arrangements, 1,4, 1,2, they're more stable if they're trans, because then they can both be equatorial. So this diastereomer and its enantiomer would be more stable than the original molecule we did. The two enantiomers will be equally stable. I don't know if I can. That was complicated, wasn't it? They tell you. So we did all this teacher training after, over the summer. And the really funny thing about that, you'll think this is hilarious given how much you're paying. Like, hardly any of us got any teacher training ever. Right? I did a PhD. Man, there were some bad looks there. Right? I got a PhD in chemistry. I was really good in the lab. Can you teach? Yeah, I assume. I've been in class. I've been going to school for 27 years. I bet I can teach. I'm better now than I was then. So anyway, they tell you like bullet points, speak clearly, slowly. That was a really important thing I said, and I said it like super fast. So let me back up. All right, so I think it was about relationships. So 1, 2, and 1, 4, right? So 1, 2, 1, 4 on a cyclohexane. Both of those groups can be equatorial if they're trans. So like this molecule, right, the achiral one, there is a more stable diastereomer of this molecule. It's an achiral molecule, but it can be cis and trans. This is cis. The trans, because the two substituents are 1, 4, would be more stable because now both of those groups can be equatorial. You can see that in the chair, right? If I do a chair flip, the OH becomes equatorial, but that isopropyl then becomes axial. So I'd need to move the OH here, leave the isopropyl where it is. Again, if you change one chiral center and leave the other one the same, you've drawn a diastereomer. They're not really chiral centers, but you get the point. Yeah.
Another thing, when you have molecule that has that many substituents on it, how do you assign cis and trans if they're...
That's an excellent question. Cis and trans only refers to the relationship between two groups. So this one, we can say this is cis 4-isopropyl cyclohexanol. The diastereomer would be trans. This one is not cis and trans. All right? You might hear somebody colloquially say that's all cis because they're all up. Like every relationship is cis in that one. But if you have more than 2 substituents, it's not cis and trans. What you have to do is specify R and S. And we're coming up on that. I'm putting it off, but all right. We've drawn one now, a diastereomer. Again, you can draw a diastereomer just, the easiest thing is to draw the same molecule, change one wedge to a dash. There you go. Constitutional isomer, just move something. I'll do resonance structure last. Well, actually, let's do the resonance structure. The reason I put this negative charge in here, the only reason I put this in, is you can draw that resonance structure. Okay, so when you're looking at this, you've got kind of a trivial resonance structure with the pi bonds. You can always just take, right? I can just take 2 electrons. I can move them to one atom. That's going to leave one atom positive. The other atom will become negative. Quite a few of you I saw on the resonance worksheet said something like, you can't split electrons. You can. And there are reactions that we'll see where a molecule has a single electron. So electrons don't have to exist in pairs. Those molecules where you have a single electron are pretty reactive. They're called radicals. You get a neutral atom, but having a single unpaired electron makes them really reactive.
So, like how you just showed like the resonance structures, and if you have like a massive molecule like that, would we be okay to just draw a resonance structure like that?
I would probably do something like this and say this is C4 or something. You're not going to have that massive a molecule to draw a resonance structure on. But yeah, like, and we do this a lot. Like, if I'm standing at if I was going to do chemistry on this thing, and I'm talking to my colleagues or my grad student, like, I am not drawing this whole thing every time, right? And this is why we call them functional groups. Like, I'm drawing the thing down here that's going to react. And I think you guys can see this, right? There's a negative charge down here. This is the reactive bit of the molecule. I'm just going to say R for all this other stuff. Like, through any reaction down here with this negative carbon, nothing's going to happen up here. So just leave it the same. Yep.
Also, I was just, this is kind of a side note too. I was doing like the nomenclature thing, you know this?
Yeah.
That's like really hard.
I said that in the email. You asked for more problems, all right? I am not inventing more problems at this point. So
But they're gonna be easier. It's like that was like a big like.
it will be an alcohol or it'll be a straightforward molecule. Yeah. Like I said, count the carbon chain, figure out the numbering of the substituents, put them in alphabetical order. Like this descending, R and S will be important, but I'll also say in there like you have to do absolute configuration, and we're getting to that. And then, what was the other thing? Yeah, alphabetical order of the substituents. Dashes separate letters and numbers. Commas separate numbers. I'm not super worried about that. That was a. So I don't know if you noticed, but I used to give these 3 assignment sheets, and it just doesn't. You will get them all as practice, but it wound up being like this massive pile of grading at the end of the semester. Again, like that's not pedagogically sound. So it was 50 points, and it was meant to be sort of an all semester. You'd work on it a little bit of a time.
Yeah, that like struck straight in my confidence. Like I was like, I'm gonna fail Thursday.
Excellent. You asked me for extra problems. It's just like, here's my. Actually, one funny story. You guys need a breather. This has been a lot. You guys watching at 1.75 or 2 or what? So everybody's nodding. That's not good. Does my pitch go up when you do that? Like, no. Okay, that's too bad. So anyway, one semester. Generally, most of the tenure track faculty at WIG teach 2 courses in chemistry. Teach 2 courses a semester. So right now I'm doing this class and I'm doing 122 lab. So one semester I was doing a grad class and 122. And they both had an exam in the same week. And somebody's like, do you have any more? This is pre-camp. This is like 15 years ago, right? And it was just like nobody had anything. I had no online presence at all. Somebody emailed and was like, do you have any more practice exams? And I switched in my head what class they were in. I'm like, oh yeah, sure. And I emailed the poor bastard like 10 old reactive intermediates. Like, I mean, he was he came from his dorm to my office and was like, I haven't studied any of this. And I'm like, you got to work hard, you got to be focused, you got to be organized. Then he showed it to me. I was like, oh, yeah, sorry. Okay, good. Funny, we're all clear now. So take a moment, if you haven't already, take a moment to figure out R and S for these chiral centers.
Actually, so since all of them are like wedges, so they're like forward, could we just say like, so because of that, all of the hydrogens are back?
All the hydrogens are back. I think that's what I was thinking when I did this. We could do, I tell you what, do R and S, do it for the original molecule. I don't want to change anything now. And if you have that, let's do a slightly more difficult one. Figure out if that's R or S. If you've got the other ones, we'll do that. We'll do that at the end. You guys at home that are watching fast, you can do that one now. Has everybody done the top one? What is that, C1? I should have told you what order to do them in. And I'm worried I'm going to, oh no, good, all right. Oh crap. My little cheat sheet is confusing me. All right. So, what I thought you were going to ask, and I was worried because I've had this question before, like they're all wedges. So yeah, the H is back on all of them, which is convenient. Like that's going to be the easiest one to figure out. I'm not saying it's easy, but that's the easiest one to figure out because you're not going to have to rearrange anything. But I've had students say like, oh, they're all wedges, so doesn't that mean they're all going to be the same? And it doesn't, because you don't know where the other things are. Right? So you can't just say a wedge is R, a dash is S, something like that. Okay, so let's go into this. H is going to be 4. This is this carbon chiral? It's bonded to a C, a C, a C, and an H. The C's all tie. This carbon is bonded to 3 C's. This carbon is bonded to a C, an H, and an H. This carbon is bonded to a C, an H, and an H. All right, carbons all tie. This is why it's important to arrange the next 3 things by atomic weight. All right, so now this carbon wins. So this is 1. This whole group is 1. You don't want to. You've got to go 1 atom at a time, but then you should think about it as, like a group is priority. H is tie. H is tie. So we got to go on. Now this carbon is bonded to a carbon, and an H. CCH. This carbon is bonded to an O, a C, and an H. O, C, H. O beats C. So now O beats C. This is 2, and that's 3. I went through that really fast. I felt like that was fast. Everybody followed it? Okay. So now then, 1 to 2 to 3. That's a clockwise circle. 4 is back, so that chiral center is R. Yep.
So if 4 wasn't back, what?
So if 4 is forward, take the reverse of your circle.
Okay.
All right, so 4 being back is the easiest. Again, like I said, I'm not saying it's easy, but 4 being back, you have to do fewer things. 4 being pointed at you, second easiest. All right, all you got to do is remember it's reversed. Because, right, if 4 is pointed at you, to arrange the molecules that, let's say we have, right, so if I have that, well, I just got to turn it around 180 degrees. And if I turn it around 180 degrees, spin around this axis, 2's coming over here, 3's coming over here. And now I have what I need, 1, 2, 3, right? So you can do that kind of in your mind. If 4 is pointed at you, do all your priorities, counterclockwise, clockwise, and just take the reverse answer. This is another reason, I haven't done one of these. You might see them on old exams. Another pretty common question is like, draw, like this would be like a nomenclature question, like draw R2-butanol. And a lot of times when I see people do that, they're like trying to figure out in their mind, like dash or wedge. Before, just draw it with a wedge, right? There's one chiral center. Draw that chiral center with a wedge so that the H is back. If it turns out to be S, you don't have to recalculate anything, right? If the wedge is S, dash is going to be R. All right, the big question is, and that's like this molecule, what if 4 is neither towards you or away from you? It's to the side, it's down, it's up. You're going to have to redraw something. Okay, so there we did. I can do, like everybody seemed to follow that one. I'm going to redraw this molecule. The other interesting thing here is you really don't have to draw this other stereochemistry. I'm doing it, but like to figure out the chirality, the absolute configuration of this carbon, doesn't really matter if this is a wedge or a dash or what, right? It just matters what direction you go. Let's do one more. Do this one if you haven't already, and then we'll move on to the harder one up there. Do the one with the methyl group on it if you haven't already. All right, you can keep working if you want to, or you can watch. All right, so again, the H is back. That's nice. That chiral carbon is now still bonded to 3 carbons. All right, so carbon, carbon, carbon. The methyl's bonded to H, H, and H. All right, that's going to be lower than everything else. This carbon is bonded to a carbon and 2 H's. This carbon is bonded to a carbon and an H. So carbon beats hydrogen. Carbon beats hydrogen, so the methyl is 3. Carbons tie. Carbon beats hydrogen, so this is 1, and that's 2. I think you guys can see, like, even if you have all these down cold, like all these rules and how to do it, and you're excellent at it, it's pretty easy as you're going through there, especially, you know, like, look, your blood's going to be pumping a little bit Thursday, times of the, you know, it's easy to kind of be like, I did that. I was like, C beats H, so that's 2, I don't know. All right, so 1, 2, and 3. 4 is back, so 1 to 2 to 3 is counterclockwise. Look at that, that's an S. All right, so if we come over here on the original S, I don't want to do that in black, I want to do it in a different color. The one with the methyl is S, and the others are all R, I think. R, 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 S. Okay. Before we move on to that last absolute configuration, all right, we've got that. Anybody questioning that? What? Yeah, go ahead. I did. Can I? You want me to do this one? Yeah. Let's. Okay, that's cool. I like to. I mean, with a whiteboard, it's really easy. I like to redraw it, and I would recommend you guys use scratch paper for these and redraw the molecule if somebody cruelly asks you to do more than one. Because you start writing 1, 2, 3s, and 4s all over the place, and they pile up on each other. And you just look at it wrong. So starting over the clean molecule is a little easier. Okay, so.
Do you also even isolate the chiral atom, like get rid of all the other stuff?
You can do that if you want, yeah. But make sure you don't get rid of so much that you lose track of what it's bonded to. Like I said, drawing in these wedges and dashes, like on this one, the only wedges and dashes I need to draw are these 2. Okay, so 4 is the hydrogen. Again, carbon, carbon, and carbon. That's a tie. So we go to this carbon, 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 H. This carbon, this might be the thing. So this carbon's bonded to an H and 2 N's. So this now is like accounting, right? Actually, Coningold Prelog is all accounting. It's not, there's nothing magic about it. There's nothing chemically real about it, I mean. So 2 bonds to the nitrogen. This carbon is technically, for Coningold Prelog, is bonded to an N, and an H. And then this carbon is bonded to an O, a C, and an H. Yeah, this was a good one to do. Thanks for asking this one. Okay, so how do those stack up? And I'm going to come look at the periodic table because I screwed this up the other day and it's still bugging me. O is heavier than N. So O beats N, O beats C. This is 1. Well, I hope I'm doing this right. All right, so O beats C, so this, and O beats N, so that's 1. N beats C, so this is 2. And that's going to make this one 3, right? So we don't have to look, we don't have to go down. Yep.
So, okay, I think this is one of the things that confuse me. So, like, when you have to go out and branch out to
Yeah.
It was originally on.
Sorry, you said so the 4 was here. What's that?
Okay, never mind.
We're doing a different carbon. Yeah. Yep. So that now this is going to be 1 to 2 to 3. That's clockwise. So that one's going to be R. Good. That's what it's supposed to be. Yeah, that one was a good one. And that's another reason you have to go one atom at a time. You can't eyeball it. I would have probably eyeballed it and thought double bond to N is going to win. So it's not poker, right? 2 of a kind is going to beat high card. So, all right. Here, H is back. O is going to be 1. CH2, CH, CH is going to win. So 1, 2, 3. That's also R. Okay, so here's our absolute configurations for the original molecule. Now, what's the relationship of this molecule with the original? It's a diastereomer. Do absolute configuration for that. I'll give you 30 seconds. All right, 45. Really only would have taken about 10. All right, so here's the trick. If you're actually trying to figure it out like we did over there, you can't do that in 30 seconds, right? I've been doing this a long time. That took me, I was trying to show it, but it still took me a while. But here's the thing. You've got this already. These 2 structures overlay in 2 dimensions the same. So what you've done, if we look at C1 here, we've changed a wedge to a dash. We've changed that chiral center. It's R over there. So it's S here. All right. Carbon C3 with the methyl stayed the same. That's S. C4 stayed the same. Wedge to a wedge, that's R. C5, wedge turned into a dash, that's a change, so that's S. All right. So like I said, and I won't do this. I think I scared the 1230 class. But like, if I said draw every diastereomer, I gave you the original molecule and said draw every diastereomer. Like, I can't think of anything more hideous to grade. You guys are sitting there thinking that would be hideous to do in class. That would be, I would not be able to grade that. But let's say I did that, and you drew them all. And then I said assign the absolute configuration for every chiral center. That is 16 times 4 chiral centers. 64, right? I always put that in terms of like the tournament. Like I can do up to 64. Maybe you guys, you're younger when they went to 68 and now they're going to go to whatever they're going to. Anyway, so once you've done one, really you only have to do this. You only have to do 4 chiral centers. You have to figure out manually 4. And if I did that, if I just said, here's, or maybe I gave you all 16 of them. This is the one you want to start with because you got, as you pointed out, all the H's are back. All right, and then you just see, did that one change, did that one change? So if a chiral center changes and you know that chiral center was R, it can only change to S. Likewise, if I gave you a structure, like again, this would be really long, but let's say I gave you a big, long, acyclic molecule that had 8 chiral centers in it. And then I drew it in a completely different orientation, conformation, looking at it from a different way, and you wanted to know if it was the same enantiomer or a diastereomer. The way to do that is for all 8 chiral centers in the 2 molecules, figure out R and S. Right? If If they all stay the same, it's the same molecule. If they all change, it's the enantiomer. If one changes, one stays the same. So you might only have to do two. Do two chiral centers on this molecule, two chiral centers on this molecule. If one is changed and one's different, they're diastereomers. Questions up to here? All right, so let's. This is actually a let's because I have no idea what the answer is. Do R and S for this chiral center. Can they see that? I wonder. Yeah. You guys have it? Okay. I couldn't tell if you were just like, I refuse. I'm not doing any more damned absolute configurations. All right, let's do priorities, and then I'll let you, before you go on, I'll make sure you have that. So, is that there's one chiral atom. This atom is chiral. Again, don't look at the wedge and the dash. Make sure it's got 4 different things on it. You can do that pretty quick. N, C, O, and O, and this is an O-methyl, and that's an O-ethyl. So that's 4 different groups. All right, so priorities, oxygen beats nitrogen and carbon. The lightest one is carbon. So this is 4. Nitrogen's going to be 3. And then O's tie, carbon ties. This carbon is HHH. This carbon is CHH. So this is 1, and that is 2. I think. Again, I'm 50 years old, and I got to look at the periodic table. All right. So there you go. And so this is, just before you get going, the reason this one's hard is not it's a weird-looking chiral center, right? It's got a bunch of funky groups on it. It's hard because 4 is straight down, okay? So there's no, I can't say, like I can do 1, 2, 3. And you might do that and be like, well, that's clockwise. You're essentially just guessing at that point, okay? That is 50-50. Because really this O-methyl, and this O-methyl sits right in front of the O-ethyl. I could have easily drawn the dash O-ethyl over here and the wedge O-methyl here. And that would change your 1, 2, 3, but it wouldn't really change anything about the molecule. All right, so you're going to have to reorient the molecule. Yep.
I actually got it figured out.
Okay. All right. People good? 1 minute? Just ready to go eat? All right, so what I would do here, since you're going to have to reorient the molecule, reorient it so that 4 is back. Right? It doesn't make any sense to reorient it so that 4 was forward and then have to reverse things. Unless, for some reason, that is an easier thing for you to do. If it is, fine. Just remember, R, clockwise is R only if 4 is back. So I'm just going to take this molecule and I'm going to pull it down like this. All right? That's going to take the 4 group, which is a propyl, straight back. And when I do that, so there's my chiral atom. 4 is in the back. 1 will come up here, tip it forward like that. 3 will do that. 2, which is in front here, is just going to tip down to there. That's counterclockwise, so that's S. How many said S? How many said R? Other people are unwilling to. Tell you what I'll do. could also imagine looking down. I've done that. So if I look down on it, I've got 1 here, 2 here, 3 there. Yeah, that's counterclockwise. I'm pretty sure I'm right. All right? But I am not 100% sure I'm right. I will freely admit that. I will check this on ChemDraw as the video file uploads. If I'm wrong, I will send you an email. If you don't hear from me, that's S. I'll take a few questions. I haven't really done much of that. Yeah.
Can you also draw Newman from the upper right perspective, so the 4 would be back?
Sure, yeah. I kind of did that in my, I don't know if you probably didn't see that, right? I imagined I was looking down on the molecule.
Wouldn't one be on the right if you're looking? Oh, I see how you're looking at it. Actually.
Yeah, so I'm looking, 1's over here, 3's over here, 2 is down here. Yeah. So don't copy off each other on the test. That seems like a obvious one. You're not allowed to look at other people's tests. But don't be distracted if people are seriously, look at everything we've done here, look at everything I've done. There's a little bit of physicality to it. So if you need to do that, do it. COVID era is perfect for that, all right? I've given exams in here where there's like 70 people in this room. And everybody's looking at everybody else, right? And it's R and S. You don't have to, I don't ever make people show their work. R. What you're betting there, though, I just want to point out, if you do that, what you're saying is, this dude next to me, maybe you know him, maybe you know they're really good, but, right? This person next to me, who I didn't know a month ago, they know how to do this. I'm confident. You've already got a 50-50 shot, right? Believe in yourself. Other questions? Anything else? Yeah.
Do you have any tips on identifying chiral centers? I struggle with that.
So, obvious things first. Methyls are never chiral. CH2s are never chiral. All right, so the first thing, as you look at these, if we just look at this molecule, 2 and 6 are not chiral because they only have 2 bonds shown. So if a carbon's only got 2 bonds to it, can't be chiral. There's going to be 2 hydrogens there. If there are 3 things bonded to it, it probably is chiral. There's a really good chance it's chiral, and you should look at it. Okay, so this carbon, there's a wedge there. Wedges and dashes tend to suck people in. A real common mistake might be a molecule that looks like this. Right? And everybody's like, oh, that's a chiral center. It's got a wedge. Right? Methyl. That carbon has 2 methyls on it, so it's not. But none of the other ones are. Right? Just at a glance, methyl's not chiral, CH2, CH2, CH2. Those aren't. That's the only one you really need to look at. And like I said, the odds are really good if there's 3 things shown to a carbon. If there's just 3 bonds to a carbon, odds are reasonably good that's going to be a chiral atom. Which only means you need to examine it more closely, right? So, is that a chiral atom?
I'm not counting that.
Whoa. So that's where you want to cheat. And no, seriously, group work, not exams, but group work, I do this with my wife all the time, right? If I put paperwork on the table and ignore it, it gets done. Right? I can do that. I can fill that form out. She doesn't like a cluttered house. I am way lazier than my wife. Orders of magnitude lazier than my wife. So, all right. 1, 2, 3, 4, 5, 6, 7, 8. Whoop. That's a chiral center. So that's what I mean. The only carbon in this molecule you need to look at is that one. All the other ones have 2 carbons on them, or 3, or sorry, yeah, all the other ones have 2 bonds shown, or 1 bond. So if you see an atom that's got 3 bonds or 4 bonds, look at it. And then, go to the end. Like that, yeah, that would be a pain in the ass to put on an exam. But, I mean, honestly, right, if this was like 500 carbons, and that was 501 carbons, that's a chiral atom. Now, physically, we didn't get to optical activity, and so really, you're not responsible for it. But one of the earliest ways we discovered enantiomers behave differently, like I said, 2 enantiomers will behave exactly the same unless they're in a chiral environment. And it turns out that plane polarized light is a chiral environment, right? So enantiomers, chiral molecules rotate the plane of polarization. If that was 500 on one side, actually that molecule itself probably would not rotate plane polarized light very far, because there's not a lot of asymmetry in that carbon, right? So anyway, that is not bankable. So humans still don't have good ability to predict which molecules will rotate plane polarized light, clockwise, counterclockwise, how much. But generally, the more different the groups are on the carbon, the more you get rotation. Okay, the only other tips I have, and this is pretty ironclad. So I've been doing organic. I taught at 12:30. I did lab from 2 to about 5:15, and then I came here. All right, I'm fried. So as you guys study in short blocks, 45 minutes an hour, study something else for a bit, get up and walk around, play a game. I know your social life is restricted at the moment, and I'm not advocating you break COVID protocol, but like walk around, stretch, do something. The other thing is, on Thursday, like don't stay up all night tonight studying and then stay up all night tomorrow night. Don't stay up either of those nights, all right? Sleep normally. Your brain is like, it's not a muscle at all. There's probably biology majors in here that won't like me saying that, but your brain it works physically. I know there's spiritual, there's all that stuff, right? It's mental. I'm fried, sorry. But your brain will work better if it is rested and fed and sober, with the exception of caffeine. Caffeine will make it work better. So, don't stay up all night Wednesday night studying. I know you will feel that urge. Some of you will feel that urge. If you're behind, you got a lot of work to do. Like, do a lot of work. But if you come in 12:30 and you got 2 hours of sleep and you didn't eat breakfast, it's not going to go well, all right? So take care of yourself physically. Physical health will lead to good academic health, or at least it doesn't hurt. All right. I'm going to see if I can remember how to turn my camera off.
We don't have to worry about enantiomeric excess.
Yeah, that's that whole optical rotation and enantiomeric excess. We will probably talk about that a little bit. I don't know if we'll talk about that or not. It is a little bit archaic, and at the same time, there's a really cool story with it. Not now, but like after the exam, maybe read that section. There's some cool stuff with it. Yeah, and that's the other thing. The other tip. These guys missed it, sorry. Big tip. If you haven't done this yet, there are old exams. I would start with the newest, the most recent. Work at least one of those like an exam. And if you can do it tonight, that'd be great. If not, early tomorrow. Like sit down, block off 75 minutes, close note, close book, scratch paper, work it. Grade yourself honestly. And, hey, I do RNS really well. I recognize isomers really well. I can't go from a chair to a bond line. So you don't have to, if you've got absolute configuration, it's not going to leak out of your brain, right? Spend Wednesday night working on chair to bond line. Or if you got chair to bond line, you can't do RNS, work on that. Like you can't study all of this stuff tomorrow night. So trust that you know what you know and work on the stuff you don't know.
Thank you.
You bet. See ya. You bet.